Hello everybody, welcome back to yet another video of FikarNot.com, now FikarNot from studies. So today we're going to be starting not exactly a brand new chapter, but the revision of the chapter Laws of Motion, chapter 3 in the physics textbook. That's Concise Physics for class 9 ICSE board. This is a board class normally because ICSE has come up with a new rule that you'll have to give boards in ninth. But of course, with the current situation, we do not know. But let's see what the future holds. But we've always got to stay prepared. So here I am making a video for all of you for the revision of laws of motion. It's one day before the exam. You don't have time to go through all the chapters. You need to revise all the chapters, and you cannot go through videos 1 hour, 2 hour, and all of that. So what do? Well, you come to this video and get a quick revision. Normally we try to finish these revisions in a single video, but hopefully, literally just fingers crossed, hopefully we are able to finish it in one video, if not 2 videos, and that's it, we're done. Okay, so we don't have time to waste. Let's get into the video. We're changing things a little bit. We'll use the orange pen this time for the important things, and the green pen for the just read through things. For the people who are new to my channel, hello there, welcome to FikarNot.com. This is, and welcome to the revision video classes. So just I'll tell you little rules. Whenever you come to the revision video classes, you have to use 2 pens. That's one for the important things and one for the non-important things. That is if you have highlighters. Normally we use yellow for important things and green for non-important things, as in just read through things. But today we are going to replace the yellow with orange, because honestly currently that's the only pen I have. So okay, so we don't have time to waste. Let's get into the video, right? Okay, starting off with contact and non-contact forces. The effect of force. We are familiar that a force, when applied on a body, can produce the following 2 main effects. It can change the state of rest or of motion of the body. That is, it can produce motion in the body. We know that force is something that can change you. As in, if I'm sitting over here, if an external force is applied, right, I can basically just fall off a chair. That is the effect of force that is in our life. So it can change the state or rest of motion of any body. It can produce motion in the body. Examples is the push exerted by a broom, a ball lying on the floor. It basically, all of that is nothing but force. Even the force due to gravity, that's the earth's pull, makes the apple fall on Newton's head, remember? So when a force is applied on a pedal by a cyclist, the speed of the cycle increases. A freely falling object continuously gains speed due to the earth's pull acting along its direction of motion, basically. So all of these are just some all of these are just some examples of force acting. So over here, nothing to mark in orange as of now. You can just mark the examples in green, just to read through if you want to, because you may get okay, is this force or not force? Even though that's a common sense question, you can still mark it if you want. I'd suggest if you mark it, just in case, it will save that much time for you in the exam, because you exactly know you've gone through the example, so you know if it's force or not force, if it's contact force, non-contact force, all of that, basically. Then the second effect of force that we see is it can change the size or shape of the body. That is, it can change the dimension of the object we know, like stretching a rubber band and all of that, loading a spring, hanging it by a rigid support, and then pulling it. That is changing the size or the shape of the object. And first one that we saw is it can change the state or the rest or state of rest or of motion of the body, basically, right? So the effect of force, that's 1 and 2, mark that with orange. 1 and 2, and just mark effect of force in general in orange. Okay, now next page, let me zoom in for all of you. Note, a force when applied on a rigid object does not change the interspacing between its constituent particles, and therefore it does not change the dimensions of the object, but causes only motion in it. On the other hand, a force when applied on a non-rigid object changes the interspacing between its constituent particles. So what do they mean over here? A force when it's applied on a rigid object, like a very rigid object, like a very hard friction creating object, right? It does not change the interspacing between its constituent particles, and therefore it does not change the dimensions of the object, but it only causes motion in it. So if I'm pushing like a ball, not a ball, a ball, okay, like for example a very rigid ball, I'm just allowing it to move and change its state of motion, or just start rolling instead of just being at rest. I am applying force on it so the motion keeps going, but because it is a rigid object, so I won't exactly change its dimension, right? But on the other hand, if I take a non-rigid object, right, if I take a non-rigid object, it also changes the interspacing between its constituent particles, and we know when it changes the interspacing between its constituent particles, dimensions will also change. So this is something you need to mark in orange, right? Mark it like 100 times, because this is very important. So you can mark on a rigid object, does not change interspacing, does not change dimension, but causes motion. And on the other hand, on a non-rigid object, changes the interspacing particles, therefore changes dimensions and also produce motion in it. You can mark all of this. Okay, so a force is that physical cause which changes or tends to change either the size or the shape or the state or of motion of the body. So this basic definition of force not only tells you about the definition, of course, but it also tells you about the two examples that we saw of the effect of force. That is the change of the state of rest or motion, or also furthermore the right. It also tells you about the effect of motion, the effects of force, the effects of force. So that is the state of rest or of motion of the body and the size or shape of the body. So you can either remember both the effects of force and derive the the definition, or you can remember the definition and then from there you can break that down and get the two effects of force. So then what will become force? A force is that physical cause. Mark that. Is that physical cause. In fact, you can mark this complete definition in orange. Okay, a force is that physical cause which changes or tends to change either the size or shape of the body or the state of rest or of motion of the body. Okay, now in kinds of forces also you have two kinds of forces, that's contact and non-contact forces. Mark in orange. Now, contact forces, the forces which are applied on bodies by making a physical contact with them, are called as contact forces. You can mark this in green because honestly by the name itself we can understand what contact forces is. Of course, the forces is basically touching the object that it's applying the force on. So forces which are applied on bodies by making a physical contact with them are called as contact forces. You can mark it with green, but you can also mark it with orange. It depends on you. Depends on how much you've understood about force until now. Hopefully you've understood a lot, but again it depends on you. Also, I'm very sorry. I have very sore throat right now. Hope you're able to understand everything I say. So these forces are produced and experienced when a body comes in contact with one another. The force of friction, a normal reaction force, force of tension, force exerted by a spring, force exerted on two bodies during collision, etc. These all are examples. You can mark it in green. Not that important to go through. Not that important to learn. Just you can just read through it basically. One night. In fact, I'd suggest all the green things that you see over here. Say if it's morning right now or afternoon right now. Whenever you're sleeping in the night, before you sleep, just open your textbook. Just go through all the green things, and then you can sleep. So it's almost like a little storybook before you sleep at night, and then you can just go through all of this and sleep. And if it's night right now, in the morning, freshen up, and while you're eating breakfast or something like that, you can just go through it quickly. Okay. And if you're eating breakfast right now and your exam is in 2 hours, I really cannot help you, my friend. I'm very sorry. Well, hopefully you're not doing that. I trust you all. Okay. So first one is the frictional force. So when a body slides or rolls over a rough surface, a force starts acting on the body in a direction opposite to the motion of the body. Along the surface in contact, this is called as the frictional force or the force of friction. When a book is placed on the tabletop is pushed to the right. The force of friction acts on the book towards the left. This force comes into play as soon as the book tends to move and resist the motion of the book on the tabletop. So you can almost say they're like battling forces, okay? So what happens is you have a ball. Let's say you have a table over here, and there's a ball moving like this in this force. So the friction acts here. So these two forces, they battle each other in such a way that it results in frictional force. So basically then what is frictional force then? When a body slides or rolls on a rough surface. Rough surface is always important. So you can go ahead and mark that with orange, okay? So when a body slides or rolls on a rough surface, a force starts acting on the body in a direction opposite to the motion along the surface in contact. This is called as frictional force. Okay. Then we have normal reaction forces. So when a body is placed on a surface, the body exerts a force downwards equal to its weight on the surface, but the body doesn't move or fall because the surface exerts an equal and opposite force on the body normal on the surface, which is called as normal reaction force. So basically, let's say I have a piece of block kept on my palm. Okay, now the block is exerting pressure downwards on my palm, right? And the reaction due to the force on the palm is going upwards. Thus, these two contact forces, they cancel each other out, and there is no force happening as a result of that. So when a body is placed on a surface, the body exerts a force downwards equal to its weight on the surface, but the body doesn't move because the surface exerts an equal and opposite force. This is called as normal reaction force. Normal reaction force, because this is what the does to us as well. If I'm walking or I'm just standing at a place, there's gravitational force, or there's a force acting downwards due to my weight, but the surface is also applying an equally opposite force. Thus, I do not move unless and until I want to move, right? Similarly, you have the tension force. Tension force is applied through strings. So when a body is suspended by a string attached to a rigid support, the body, due to its weight W, pulls the string vertically downwards, and the string is stretched. In a stretched condition, pulls the body upwards by a force which balances the weight of the body. So basically, when a body is suspended by a string, suspended as in attached by a string, and it is attached to a rigid support, the body, due to its weight W, pulls the string vertically downwards. So it is pulling the string vertically downwards because its weight is so much, right? And in its stretched condition, pulls the body upwards by a force which balances the weight of the body. So due to its weight going upwards in a stretched condition, due to its weight going downwards, due to its stretched condition going upwards, balancing it out, and the weight of the body, this force which balances the weight of the body, and this force is called as tension force. You can see this is different. Normal reaction force is where you are on a flat surface. This is where you are applied, through strings, and there's a tension between the rigid support and also the weight that is pulling the object down, but it won't, because both of these forces are balancing each other out. But in cases where the force or the weight is too much, of course it will fall down, because both the forces are not balancing each other out. Now, next one, force exerted by a spring. So let's look at this picture over here. Consider a spring with its one end kept fixed if it's either let me say this again. Consider a spring with its one end kept fixed if its other end is either stretched or compressed. The spring exerts a force F opposite to the direction of the displacement of its free end. The magnitude of this force is directly proportional to the magnitude of the displacement, that is the elongation or compression. This force is called as the restoring force. Now, what happens is, let's say I have a fixed end over here, and I have a string that is over here. So if I'm pulling the string this way, right, that's the displacement, and let's say this is the amount of displacement that the spring went through. So if I'm pulling the string away from its fixed end, I'm basically just pulling it, and there's a certain amount of displacement that is happening between the string. Now what happens is, the string applies an equally opposite force equally opposite force opposite to the direction of the displacement. So thus this force and this force, they cancel each other out, and that's a restoring force. Like a spring balance works on the principle or shape. It does not exert any force on the object attached to its ends, but if the spring is compressed, it pushes away the object with a restoring force at its end, while if the spring is attached, it pulls in each object with a restoring force F at its end. Hope you all understood all of this. Okay, then the fifth one. Force exerted due to collision. When two bodies collide, they push each other. As the result, equal and opposite forces acting on the body. These forces are the forces of action and force of reaction. A body B, while in motion, collides with a moving body A, exerts a force AB on the body, which is called the force of action. At the same instant, body A also exerts a equal and opposite force on F, a force of reaction FBA on the body B. As the result of two forces, the two bodies move apart after collision. So basically, let's say you have a ball A and you have a ball B. Okay, now what is happening is both of them are colliding with each other like this. Okay, so the force on A due to B, when B is colliding with A gets a force of AB. When A is colliding to B, they get a force of BA. Now both of these forces are coming in the same direction. One is here, one is here, different directions actually, and then therefore they go and leave like this as well. Simple as that. Okay, and this was all about contact forces. Now let me just tell you what all is important until now. First thing important over here, contact forces as a whole. Contact forces is when the two bodies come in contact with each other and they make a physical contact with each other. As I said, you can mark it in green if you want, common sense. If you can mark it in orange as well if you want. Okay, then frictional force. Mark that when a body slides or rolls and then there's an equally opposite force. Normal reaction force also makes sense. Exerting force, then forces like this, right? Then a tension force also makes sense. Same, so mark that as well. Then on the next page, mark the force exerted by a string. And in this case, you can also mark the example. Like you can get a spring balance. What force does it work on? Works on force exerted by a spring. So you can mark that as well. Then force exerted due to collision also is same. So you can mark the force FAB and FBA and all of that. Right? And that's it. Done. Okay, perfect. Now let's move on to non-contact forces. So the forces experienced by bodies even without being physically touched are called as non-contact forces, or distance, or at a distance force basically. Now, non-contact forces are those forces, basically the forces experienced by bodies even without physically being touched, as I said before. Examples: gravitational, electrostatic, and magnetic force. So basically in universe, each particle attracts the other particle due to its mass. This force of attraction between it is called as gravitational force. So basically the Earth's pull on us. If we're able to walk on a surface, it is because of gravitational force. If there wouldn't be gravitational force, we would basically be flying in the air like people are in space. So the Earth also, because of its mass, attracts all other masses around it. The force on a body due to the Earth's attraction is called the force of gravity, or the weight of the body. Basically, the Earth also, okay? Earth also has such a huge mass on it, so it attracts all the other small masses, because we are comparatively a very, very small mass in front of the Earth, right? We are like a small insect, of course. So the force on the body due to the Earth's attraction is called as the force of gravity, or the weight of the body. It causes motion in the body towards the Earth, that's downward, if the body is free to move. Thus, it is the force due to gravity that makes a body fall when released from a height. The body also attracts the sun by an equal force. There is no motion caused in the Earth because of its huge mass. So basically over here you can mark the definition of gravity in orange because that is important. So what is gravity force? Basically, just you can remember this, when there are two masses, right, in our earth, whenever two objects attract because they have different masses, it is because of gravitational force. Similarly, the earth is also a huge mass, so it attracts all the other masses towards it. This results in the Earth's gravitational force. This is because, and the gravitational force results in us walking on a surface and not exactly flying in the air, right? And the force on a body due to the Earth's attraction is called the force of gravity or the weight of the body. Right? It causes motion in the body towards the earth, and that's why when a person is released from a height, that person basically almost gets a lot of injuries because that person cannot fly and save himself or herself, right? Examples, again, mark it with green, not very important, but worthy enough to go through. Then you have the electrostatic force. Two like charges repel when two unlike charges attract each other. The force between the charges is called as electrostatic force. This force acts between the charged objects even when they are separated. Basically, you can say when two like charges, if we say that's plus and plus, they repel, but a minus and plus will always attract, right? So this is known as electrostatic force, and the force between these charges is known as electrostatic force, something you can mark in orange. Okay. Now, for example, when we take a comb and it is rubbed on dry hair, the hair gets charged and it becomes like completely like it basically just stands up like this, like an electric shock, right? So if this comb is brought near the small bits of paper, opposite charges are induced on the bits of paper, and they begin to move towards the comb, and this is called as the electrostatic force. Similarly, you have something very, very similar to magnetic force. Now, two like magnetic force repel while two unlike magnetic poles attract each other. This force between the magnetic poles is known as magnetic force. This force acts even when the magnetic poles are at a separation. For example, if I have a little pin that is lost in my bag, I can just take a magnet and attract the pin towards the magnet because it will have a magnetic force applying on it, basically. Now, general characteristics of non-contact forces would be the gravitational force is always attractive in nature, while the electrostatic force and the magnetic force is attractive or repulsive, as in poles repel, basically, right? Not pulses, I'm sorry. Basically, like poles, they repel. Then the magnitude of non-contact forces on two bodies depends on the distance of separation between them, decreases with the increase in separation. It decreases with the increase in separation. The magnitude decreases with the increase in separation and increases with the separation as the separation decreases, basically. Okay. And also, its magnitude varies inversely as the square of distance of separation, that is, on doubling the separation, the force becomes 1/4. Something you need to mark in orange very, very importantly. So the force becomes, when on doubling the separation, the force becomes 1/4. Okay, so the magnitude of the body when it increases, okay, it decreases. So the magnitude decreases with the increase in separation, increases with the decrease in separation. Okay, and also the force becomes 1/4 when the distance of separation, on doubling the separation, the force becomes 1/4, basically. So with this, we come to an end of contact and non-contact forces. In magnetic force, mark that in orange as well, and also the general characteristics of the non-contact forces, something very, very important. Okay, now let's finally go on to the moment you've all been waiting for, that is Newton's first law of motion and inertia. Okay, now let's move on to Newton's first law of motion and inertia. So Newton's first law of motion, in chapter 2 we have read that the linear motion We've read about the linear motion basically, right? Now the question arises, what is the cause of this motion? What produces motion in an object? It is our common experience that a force is to be applied on an object to produce motion in it. Example, to move a cycle, the cyclist has to apply force on its pedal, etc., on their pedal basically. So we know for a body to move until now, force is something that we need to apply, be it contact or non-contact, right? And we have thousands and hundreds of examples like this. But Galileo did not prove the above view from his experiments. He found that no force is needed to continue the motion of a moving body. If a body is set in motion, it will remain in motion even when the force is applied to set the body in motion is withdrawn, provided that there is no other force such as friction, etc., to oppose the motion. From our everyday life, we know that a ball is kicked. It moves a certain distance before coming to rest. In fact, it stops due to the force of friction between the ball and the ground. If the friction between the ball and the ground is reduced, by kicking the ball on the smooth road, it travels comparatively a much longer distance before coming to a rest. But if somehow it would have been possible to reduce the force of friction completely, as in there would be no external force such as friction, a car stopping it, we stopping it, probably kicking it even further, accelerating it, everything, all of that, if it's gone completely, Galileo proved that the body or the ball will still stay in motion unless and until you have an external force acting on the body or stopping the body from its continuous force of motion. Example. Let's take an example. So basically, let's say a ball is moving. The same example as your textbook said. I'll just explain this to you. So let's say a ball is moving on a straight round. Let me draw a better ball. Yeah. Let's say a ball is moving on a straight ground. Okay. Now, we until now have known that a body cannot move without applying force on it, and it will come at a state of rest after some time, right? But have you ever thought if external forces like friction or someone stopping it, all of this would not have even been there, and a body was or a ball was only running or rolling on a smooth surface with extreme, like literally zero friction, and there is no opposing force that is battling it. So what would happen? The body would still stay in motion. And Galileo proved the above view that if a ball is moving after a certain point of time, it comes at rest because there is friction acting on it. If we move it at a smooth surface, it will go a much longer way than the ground. Why? Because there is less friction, but it will still come at rest because there is still some amount of friction in a smooth road. So after some time, both the forces are opposing each other, and there is a battle happening over there. But what if the friction was completely taken out of the ball? Right? The ball would have remained in motion forever after kicking it once. Thus, it is concluded that in the absence of the force of friction, no force is required to keep an object moving after bringing it in motion. In other words, an object is, if once sent in motion, moves with uniform velocity if no force acts on it. Thus, a body continues to be in the state of rest or in the state of uniform motion unless an external force is applied on it. This is Galileo's law of inertia. From the above discussion, we conclude that if a body is at rest, it remains at rest unless a force is applied on it. If a body is moving, it will continue to move with the same speed in the same direction forever unless a force is applied on it. Like a wall comes in front, a car stays, or a car just runs over the ball, or just something like that. Or just a cyclist just goes through the ball. All of these. So, if these external forces did not exist, the ball would be moving forever. Forever, as in its complete life. Even though a ball is non-living, but just the life of Earth in general. Right? So, the things that you need to mark in orange and green over here is... okay. Examples, always, as I said, in green. And also, one more thing, before Galileo, scientists were of view that a force is needed not only to start a motion but also to keep an object moving even with uniform velocity. In other words, an object remains in motion so long as the external force applied to produce motion remains present, basically. Same thing, I forgot to read it, I'm sorry. So you don't need to mark any of this because it's just a basic, just telling you about what happened in the history. Again, the second example can be marked in green. And from the line Galileo did not prove, from there, we'll start marking things in orange. So take out your orange pen and mark no force is needed to continue the body of a moving body. If a body is set in motion, it will remain in motion even if the force is withdrawn, provided that there is no forces, friction, etc. Mark till there. Then mark, thus it is concluded that in the absence of force of friction, no force is required till a force acts on it. Completely that paragraph. And also mark, this is called as the Galileo's law of inertia. Then the first 2 points from the above discussion points, that is, if a body is at rest, it will stay at rest. If a body is in motion, there is no external force applying on it, even a bit, even 0.0001. The body will stay in motion continuously forever for its entire life, like the life of Earth. So Newton put the above observations in the form of a law, which is called Newton's first law of motion statement. According to Newton's first law of motion, if a body is in state of rest, it will remain in state of rest, and if it is in a state of motion, it will remain in a state of motion in the same direction with the same speed, unless an external force is applied on it. So Newton put all these observations. He, of course, simplified it, not simplified exactly, but added, a few numericals here and there, all of that, and he named it as Newton's first law of motion from there. So it's still called as Galileo's law of inertia, but this complete law of motion and inertia together is called as Newton's first law of motion, basically. So the qualitative discussion is Newton's first law can be understood in the following two parts, as definition of inertia, that is Galileo's law of inertia, and also the force, definition of force. So we are going to go through both of them, and we'll also mark a lot of things. Again, mark the statement according to Newton's first law of motion. Mark that complete thing in orange. Very, very, very important. This basically tells you about what Newton's first law of motion is. So if you have an orange pen right now, mark it here, basically just mark it completely. Okay, so the qualitative discussion. Newton's first law can be understood in two parts, as I said. Let's start off with definition of inertia. So in the first part, Newton's first law gives the definition of inertia, according to which an object cannot change its state by itself. If the object is in a state of rest, it will remain in the state of rest. And if it is moving in some direction, it will continue to move with the same speed. And this is inertia, basically, because this was Galileo's law of inertia, right? So it will continue to move with the same speed in the same direction unless an external force is applied on it. Example, a book lying on a tabletop will remain placed at its place unless it is displaced. Similarly, a ball rolling on a horizontal plane, it keeps rolling unless a force is applied on it. So the property of an object by virtue which it tends to retain its state or of motion is called as inertia. It is the inherent property of each object. So basically, what do they mean over here? So we saw that Galileo proved a few things about inertia. That was, a body will be at the state of rest if there is no force applied on it, and it will stay in motion once a force is applied on it forever, unless and until there is an external force stopping it from going forward. So the property of an object by the virtue of which it tends to retain its state or rest or of motion, basically the property of an object by the virtue of which it tends to retain. An object always tends to retain its state of rest unless and until I move a book in front of me, it will try to retain its state of rest. It will stay there. That won't be exactly, even if today, let's take this example. If today I'm alone at my house, home alone, and I am really, really scared because there's no one with me in my house. And I have a book just kept on the tabletop. The book moves and falls by itself. I would definitely think there is a ghost at my house, or someone is playing a prank with me. Why? Because the book cannot move by itself. It tends to retain its state of motion, right? It tends to retain a state of rest or of motion. And this property is called as amnesia. So if ever in exam if you forget the definition of amnesia, just think about a book falling by itself. You'll get to know that an amnesia is the property by which an object tends to retain its state of motion or its state of rest. It is the inherent property of every object. Since it is also not a living being, it cannot move. So an object tends to retain its object. It doesn't do that on purpose. Since it's non-living, it has to. It does that just by itself, basically. So that's the property of amnesia. Then this was the first half. What about the second half? That is the definition of force. The second part of Newton's first law defines force, according to which force is that external cause which can move a stationary object or which can change the state of motion of a moving object. So now, we saw that if a body is at the state of rest or motion, it will remain in the state of rest. That is the first half. Second half says that if the body stops moving, it is because an external force is applied on it. And if an external force is not applied on it, it will remain in the state of motion. So that basically says about the definition of force in this. That force is that external cause that can move a stationary object or can change the state of motion of a moving object, like basically just stopping it. Thus, the force is qualitatively it is defined as force is that external cause which tends to change the state of rest or the state of movement of a moving object. Something you need to mark in orange. Both of these definitions, major definitions, right over here. Definition of amnesia as well, mark it in orange. One thing to note is that force is a vector quantity. The sum of two equal and opposite forces is 0. A body acted upon its several forces can also have the resultant net force to be 0. So basically, first, force is a vector quantity, easy. The sum of two equal to opposite forces is always 0. Makes sense. That is because that makes sense, right? That is how a book on my table can still stay where it is and not move, because it is applying a downward force because of its weight, but the table is also applying an equally opposite force, which cancels it out. It becomes 0, and as a result, the book stays where it is. Then a body acted upon by several forces can also have a resultant net force, and it can also be equal to 0 in a few cases, which we won't talk about, just something you need to note, right? So you can mark this note in orange because it is pretty important. Okay, now let's talk about mass and inertia. So basically, to understand Newton's first law of motion very, very, very properly, like extremely, just perfectly, we need to talk about mass and inertia, just in little depth. So inertia is an inherent property of each body by virtue of which it has the tendency to resist the change in its state of rest or the state of motion. The property of inertia is because of the mass of the body. The greater the mass, the greater is the inertia of the body. Thus, a lighter body has less inertia than a heavier body. Because, why? Because a lighter body is much easier to move. Let's say if I have a object kept in front of me of, like, say 5 kgs, like a suitcase of 5 kgs or 10 kgs. And I similarly, beside that, I have a highlighter kept near me, the orange highlighter or the orange or the green highlighter. Now, which one will it be easier to move? or let's say I just have a feather of, I don't even know how many kgs. It's not even any kgs. It's basically in grams. So by air, that is an external force, the suitcase will not even move a bit, like even 0.0000001 millimeter. But by air, the the feather will move here and there, which just says that the greater the mass of the body, the suitcase is able to inherit its property to be at the state of rest, even though an external force is applied on it, but the feather is not able to inherit its property that well. So thus, the greater the mass of the body, the greater the inertia of a body. Thus, the lighter the body, the less the inertia. The lesser the inertia, then a heavier body. So in other words, more the mass of the body, also just mark the greater, the lighter, the all of that in orange. Important point. In other words, more the mass of the body, more difficult it is to move the body from rest, or to stop the body from or to stop the body if it is initially in motion. Thus, mass is a measure of inertia. As in, inertia depends on mass depends on inertia. Similarly, again, examples in green. Kinds of inertia and its example as illustration of first law. Inertia is of the two following kinds: inertia at rest and inertia of motion. Inertia of rest: if a body is at rest, it will remain at rest unless an external force is applied to change its state of rest. The body, this property of the body is called as inertia of rest. This is where basically basically the property of the body inheriting its state of motion unless and until there is an external force, like the ghost example that I gave you. So the body will basically just stay at rest. You can say inertia is divided into two parts: motion and rest. Rest is the first law, motion is the second law, right? So now you can mark both of that in orange as well. Inertia at rest as a whole you can mark as orange. And now the example. So these examples are something that you do not need to ignore, and you really do not have to ignore. What I'll do is basically something you just need to go through, but by yourself, because there's nothing really to explain in this, and this is a revision class, and I need to really rush because I know you all are getting very, very late. So I'm trying to finish everything over here so you can read it by yourself. Very, very important example. Mark it in orange. I'm not going through it, but I will tell you to mark it in orange because it is extremely important. I cannot stress on how important it is basically. Second one also, let me just finish the inertia of motion before we go on to Newton's second law. A body is in a state of motion, continues to be in the state of motion with the same speed and in the same direction in a straight line unless an external force is applied on it to change its state. Property of the body is called as inertia of motion. Something to mark in orange. And basically this page, that is, if you have the same textbook as I do, page numbers 62, 63 and 61. Like 61 and 62 completely and 63 at the top. All of this is extremely important. There is not even a single thing that you do not need to mark in orange over here. Everything needs to be marked in orange because everything is super, 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 super important. Cannot stress enough on the word super over here because honestly it is pretty important. All right, so just mark it, and yeah, let's go on to the second law now. Okay, so we have arrived over here. Newton's second law of motion, starting off with linear motion. So it is our common experience that if two bodies of different masses are moving with the same velocity and they are brought at rest in the same time, the force needed to stop the heavier body is more than the lighter body. You can say this is also the inertia of inertia of mass. More the mass of the body, more the inertia. Less the mass of the body, less the inertia. And similarly, if two bodies of the same mass are moving at different velocities, then to stop them at the same time, the force needed to stop the faster body is more than the slower body because it's almost going like very, very fast. So you can see over here that the inertia is something else. And I also just got to know that this complete video I was pronouncing inertia wrong. So I'm very, very sorry. I apologize for that. It is inertia. I'm very sorry. That's how I always pronounced it. I just got to know from one people, just like one person. I just got to know that I was pronouncing it wrong, so I'm very, very sorry. It is inertia. So thus the force needed to stop a body in definite time depends on both the mass of the body and its velocity. Definitely. More the mass, more inertia, or not more inertia, sorry, more force you'll need. More the velocity, more force and more time you'll need, basically. Actually, the force needed to stop the moving body in a given time depends on the product of both mass and velocity, which is called as linear momentum. Mark this complete thing in orange. So mark, actually the force is needed to stop the moving body till linear momentum. Then mark two masses, harder to stop the faster body and the one with more mass. The complete definition of inertia, inertia, and linear momentum of a body is the product of the mass and velocity, also that. Okay, so the linear momentum of a body is denoted by the letter P. The word momentum is generally used for linear momentum. For a body of mass m moving with velocity v, the linear momentum P is expressed as P equals to mv, that is m into v. It is a vector quantity. Similarly as what? Force. Yes, force is also a vector quantity. It is a vector quantity in the direction of the motion of the body along the velocity of the body. Now, from the relation P equals to mv, unit of momentum equals to unit of mass into unit of velocity, SI unit of momentum thus becomes kg ms is to the power of -1. Why? Because whenever you see -1, it basically means, let me just tell you this, it basically means kg ms. Basically this, right? kg ms. Why? Because when you move this over here, it becomes -1. Okay, so it's kg ms. Kg is mass and velocity is ms. So it becomes kg ms, and the CGS unit, very, very predictable, becomes g cms. Okay, perfect. So this is the relationship between the linear momentum and the mass and the velocity of the body. From equation 3.1, change in momentum equals to, this triangle symbol is basically called as del or delta. Before a quantity denotes a small change in that quantity, and the change in product mv can be either due to the change in mass m, or due to the change in velocity v, or due to the change in both mass and velocity. Okay, so in easier words, what they're trying to say is whenever the momentum changes, whenever the linear momentum changes, we use the sign like a triangle, which is called as delta or del. So this small sign is either used as a change in velocity or mass, and as a whole, a change in the linear momentum, that is P equals to mv. Now, in the case of atomic particles moving with velocity comparable to velocity of light c equals to 3 into 10 to the power of 8 ms. Okay, so over here what you can mark in orange is the equation of the change in momentum first, then delta, what it symbolizes, then the change in product may either be in both of them, all of that. And yeah, that's it. That should be enough. Okay, now let's move on to the rate of change of momentum. So the second section of this chapter talks about not only the linear momentum but also the Newton's second law of motion. So we are going to talk about both. So starting off with the rate of change of momentum, when a force is applied on a moving body, its velocity changes. Due to the change in velocity of the body, its momentum also changes. Let a force F be applied on a body of mass m for time t, due to which its velocity changes from u to v. Initial momentum will be mu and final momentum will be mv. Okay, so the rate change in momentum would be mv minus mu, which would be equal to change in momentum by time, which would be equal to v minus u by t. That's acceleration. But you can say m into v minus u by t. basically. So that's mass and velocity, makes sense as well, and that will be the change in momentum. But acceleration would just be v minus u by t, because velocity by time equals to acceleration, as all of you have already studied in chapter number 2. So the rate of change of momentum equals to ma, that's mass into acceleration, and yes, that's it. And this relation holds true when mass of the body remains constant. Thus, when a force acts on a body, the rate of change in momentum of a body is equal to the product of mass of the body and acceleration produced in it due to the force, provided that the mass of the body remains constant. Now let's take an example or an alternative method like written over here. For a body of mass m moving with velocity v, its linear momentum is p equals to mv, right? Now in time, that's a change in time, if its linear momentum changes by delta p on applying a force on it, then the rate of change of linear momentum would be delta p by delta t, delta mv by delta t, which equals to m and delta v by delta t. Basically, the above equation is the same as 3.4, just a bit different, like an alternative method. So you can mark this in green, but the others, that's the rate of change of momentum and all of that, you can mark that in green because that is generally important. I'd say go for like the normal one because these equations are like the common sense one, but the alternative method you can go through. They may ask you about the alternative method. That's why I'm telling you to mark it in green. Otherwise, I wouldn't have, because I'd normally go for like a more simpler equation, Okay, fine. Finally, now let's go on to the Newton's second law of motion. First law talked about inertia, and now we are going to talk about something else. So let's get into it. Okay, so Newton's first law of motion defines the force only qualitatively. A force is that physical cause which changes the state of motion of a body when it is applied on it. It means that force produces acceleration on the body. That is, the force is the cause of acceleration. Now we shall see that Newton's second law of motion gives the quantitative value of force. That is, it relates force to the measurable quantities like acceleration and mass. It is our common experience that if we push a tennis ball gently, a small acceleration is produced, and it acquires a small velocity in a certain amount of time, for sure. But if the same tennis ball is pushed even harder than the last time, a larger acceleration is produced in it. What is acceleration basically? That is velocity by time, right? So if a body is moving with velocity, and if it keeps going faster by like say 1 kilometer per hour, we would say it has uniform acceleration. And in a body that is already moving, right, if you push a ball gently, acceleration is created because from rest you are moving that body in a certain state of motion, right? And if I am even moving that body more faster than it already was, I would say that it is acquiring even more acceleration, right? And it acquires a larger velocity in the same time and interval. Thus, the magnitude of two forces can be compared by measuring the accelerations produced by them when they are applied one by one on the same body. If a force F1 produces an acceleration of 5 meters per second, and F2 produces an acceleration of 10 meters per second on the same body, the magnitude F2 is 2 times the magnitude of F1. Experimentally, Newton found that the acceleration produced in a body is directly proportional to the force applied on it. Makes sense. Force increases, acceleration increases, right? So this is Newton's second law of motion, that force produces acceleration on the body, and force also depends on, mass and acceleration also depends on the force of a body, right? So similarly, if we try to produce the same change in velocity in the same time, that is to produce some acceleration in the football and tennis ball initially both at rest, we need to apply a larger force to move it even faster than the last time, right? You can almost say, like in the first motion we said that if a external force is not applied, the body will continue to move or it will stay at rest. But what if it is applied? What will happen? This is what the Newton's second law of motion talks about. Okay? So in a similar way, now let's get into depth about the Newton's second law of motion. So basically, similarly, if we try to produce same change in velocity of the time to produce the same acceleration in a football or tennis ball, initially both at rest, we need to apply a larger force on the football than on the tennis ball. Thus, the force needed to produce same acceleration in two bodies of different masses is not the same. That's why we say mass and acceleration is both dependent on that is force, and it is more for the body of larger mass and less for the body of smaller mass. Force F to produce an acceleration of 5 meters per second, that's on a mass of 2 kgs. Basically, a few examples, you can mark it with green, you can go through it. And experimentally, Newton found that force needed to produce same acceleration in different bodies is proportional to their masses. And on the basis of Newton's experiments, he concluded that. Before we get into all of that, 1 minute. Let me see what all you need to mark in orange. Okay. First, Newton's second law of motion. Mark that. Okay. Then Newton's first law of motion defines the force only qualitatively. Physical force produces. Okay. It means that force produces acceleration in a body. That is, force is the same of acceleration. All of that. Mark that complete paragraph. Then you can mark, experimentally, Newton found that acceleration produced, so force is directly proportional to acceleration. And in the next page, you can mark larger force for larger bodies. So, force needed to produce same acceleration in different bodies is proportional to their masses. Okay? Okay. Moving on from here, on the basis of his experiments, Newton concluded that the acceleration produced in a body of given mass is directly proportional to the force applied on it. That is, A is directly proportional to F if mass remains constant. A graph plotted for acceleration is given right here. Acceleration against force F, a straight line is shown over here. And the second one is the force needed to produce a given acceleration in a body is directly proportional to the mass. That means force is also directly proportional to mass. So if acceleration remains the same, this would be your graph. Okay? And combining the equations, that is, force is directly proportional to m into A, or force equals to kma. Here k is constant. The unit of force is so chosen that k becomes 1. When m equals to 1 and a equals to 1, thus the amount of force is taken as 1 unit, and combining all of this, force equals to mass into acceleration. And this is the mathematical expression of Newton's second law of motion. Then note, if a given force is applied on bodies of different masses, the acceleration produced in them is inversely proportional to their masses. That is, A is inversely proportional to 1 by m. That is, if a force is applied on bodies of different masses. Okay, and a graph plotted for the acceleration is given right here because they are inversely proportional. And from here, we talk about the CGS and SI units of mass and acceleration, and basically of force in general, because force equals to mass into acceleration as of now in this case, and that's what Newton's second law of motion also talks about. Okay, so the force is related to mass and acceleration on the basis of the SI unit of force is Newton. 1 Newton is equal to 1 kg, that's ms. The standard unit of Newton is n. In CGS unit, it is dyne. 1 dyne equals to 1 g into 1 centimeter. And relationship between Newton and dyne given in the next page. You can mark it in orange. Very important. Just something to go through. It's very important, but something to go through because I really cannot comment anything on it. Just the mathematical expression. You can go through it if you would like to. I'd definitely suggest that you go through it. Okay? Having said so, right over here, Newton's second law of motion in terms of rate of change of momentum. So when force is applied on a body, it produces acceleration in the body, due to which the velocity, hence the momentum of body, changes. From equation 3.4, we have seen that the rate of change of momentum is equal to the product of mass and acceleration, etc. So basically over here what they're saying is they are relating second law of motion to that of momentum. So I would suggest that you can go through this. This is a very simple mathematical expression. Again, nothing really to explain. That is why I'll not be going through it, but I'd suggest that you mark it in orange or green according to, just mark it in something because it is important, very important. But again, it's a mathematical expression, so there's nothing really to explain in it. All I can do is read, and I really need to finish this video very quickly, right? Because it is a one-shot video. And the whole point of this video is that you can complete this complete chapter as a revision in about 1 hour and not take about 3 to 4 hours in a chapter. 1 hour and your complete chapter is done. Okay? So we've already reached 1 hour, so we've really got to hurry up. Now, statement is, according to Newton's second law of motion, the rate of change of momentum of a body is directly proportional to the force applied on it, and the change in momentum takes place in the direction in which the force is applied. Makes sense, right? Makes complete sense. And with this, we come to an end of this, like the second law of motion. Some examples are given over here. Something, again, you can go through, as I said with the last examples. But these examples that I said to just go through now are very, very important. A lot of give reason questions can come from here. So make sure that you go through it very diligently and very, very, very properly. Okay, we're on to our last page, 2 sides. Let's do this. All right, starting off with Newton's third law of motion now. So Newton's first law tells about being a change in the state of rest, or bringing a change in the state of rest or in the state of motion. And the Newton's second law tells us about the magnitude of acceleration produced by force when applied on the object. Now this question is answered by Newton's third law, which states, or the question is that these 2 laws do not explain on how force acts on the object. So the statement is, to every action there is always an equal or opposite action, which gives the position, gives the object the position that it is supposed to be in. Now let's take an example, like a book, lying on a table. It is acting a force downwards by its weight, but then the table is also acting an equally opposite force upwards, and that's why the book stays where it is. And even while moving on the ground, we exert force by our feet, but then the same force comes upwards. So therefore, it's all equaled out, and there is also an opposite force acting on us. So what is the explanation behind this? Why does this happen to us? Well, the explanation is, in the above stated examples, we observe that there are 2 objects and 2 forces. In the first example, the weight of the book acting on the table downwards is the force of action, and the force exerted by the table on the book upwards is the force of reaction. This means that, let's take an example as of chemistry over here, okay? So we know in chemistry we always say that whenever we apply a following action, like a chemical action, also known as a chemical equation, so when 2 substances, they go under such a chemical reaction, it results in the formation of a reaction. It results in a chemical reaction. When the action of 2 substances coming together forms 2 products, it is called as a chemical reaction. Similarly, when let's take the first example, the weight of the book acting on the table downwards is the action, right? That is the substances going under a chemical equation, right? And the force exerted by the table is the force of reaction, as in the opposing force. And over here you have a complete reaction. So in the second example, the force exerted by our feet is the force of action, and above is the force of reaction. Thus, Newton's third law of motion states, in an interaction of 2 bodies, A and B, the magnitude of reaction, that is the force AB applied to B on body A, is equal in magnitude to the action, that is force BA applied to A on the body B, but they are in directions opposite to each other. Note, the action and reaction never act on the same body, but they always act simultaneously on different bodies, A to B and B to A. That is, force of interaction are always in a different pair. So over here, explanation or you can say experimentation of this. In Fig 3.12, the ring of a spring balance B is attached to a hook fixed in a wall, and then the hook of another spring balance A is attached onto the hook of the spring balance B. Now the ring of the spring balance B is pulled, and we find both the balances show the same reading. This is because there's an opposing force applying on both, as we saw when we started the chapter as well. After this, they talk about the examples and action and reaction, again something that you have to go through, and with this, my dear students, we come to an end of this chapter. Hope you all understood each and every concept of this chapter. A quick revision comes to an end. Sorry I extended the time limit of this video by 5 minutes, but hope you all understood this video. If you have any doubts, post it in the comment section below. I'll be more than happy to solve them. Like, share, subscribe to FikarNot.com because it'll mean a lot to me. And thank you so much. Bye bye.